We said that anything made of metals conducts electricity. Anything made of nonmetals is an insulator, doesn't conduct electricity. What about an ionic compound? It's got a metal, which always conducts, and a nonmetal, which never conducts. Which one is it going to do? That's a legitimate question. We know metals always conduct. We know nonmetals never conduct. What happens if I put them together? Okay. So first of all, we have to say, what the heck is conducting electricity? Conducting electricity requires two things. Two things. Thing number one, you have to have charged pieces. Thing number two, they have to be able to move. Because that's what electricity is moving charges. So you have to have charges, and they have to be able to move. That's what it takes to conduct electricity. So, in a solid ionic compound, in salt, do the pieces have charges? Well, Na plus and Cl minus. Can they move? In a solid, can they move? No. So solids have the charged pieces, but they can't move. Those ions are locked in place. So ionic solids are insulators. Ionic solids don't conduct. In fact, if you go out here and you look at the telephone poles, you will see that the wires do not touch the poles. That in between, there's a little ceramic piece. The name for that ceramic piece is an insulator. That's the name of it. It's the insulator. And it's made out of ceramic because ceramic is an ionic compound. Ceramics are ionic compounds. So everything's locked in place. It's not going to conduct, so we don't want the electricity going through the pole. We want to keep it through the wire. So that's why they put the insulator there, is to make sure the electricity doesn't go through the pole, it goes through the wire instead. Okay? But when I melt them, then the ions can move around. Well, when I melt it, I've got ions, charged pieces, that can move. So melted ionic compounds conduct electricity. It doesn't do it as a solid, but if I heat it up till it melts, then it'll conduct electricity. Anybody ever seen that? No, you've never seen that. Why not? Why do we make our wires out of melted ionic compounds? What would you say yesterday about them melting? Really high temperatures. It's too high a temperature. You're never going to see it because I happen to find one ionic compound that I can melt in front of you. Okay? I went out of my way searching for it. Okay? And the reason why it melted fairly easily was because its crystal was so complex to build in the first place. Okay? So the problem is getting up to 800 degrees Celsius before they melt. That's a problem. You probably don't want 800 degrees Celsius stuff running through your walls. So we don't use ionic compounds for wires because it doesn't work. Okay, but there's another way to get those ions to move. Okay? The other way is to dissolve them in water. Okay? So, I'm about to try something. Kids, don't try this at home. Okay, so I got a light bulb. The light bulb is not on. Can anybody tell me why the light bulb is not on? It's not plugged in. Okay. The light bulb has been plugged in. The light bulb is still not on. Why is the light bulb not on? Well, what would explain why it's plugged in, but the light bulb doesn't come on? I can't think of a lot of explanations except the obvious one. The wire's broken. Would that explain why the light bulb? Okay. And I knew the wire was broken. I actually know exactly where the wire is broken. The wire is broken right between those two poles. See the two posts coming in? If I connect those with metal, so there's my broken wire. The light bulb's not on because the wire's gone. Kids, don't try that at home. And now here's an extreme one. Kids, don't try this at home. Water and electricity. Sure you want to be in the front row? Nothing happens. Well, the water can move, right? But is water ionic? No. Water doesn't have charged pieces. So water is a lousy conductor of electricity. That's what makes it dangerous. Because when somebody drops the hairdryer into the bathtub, you're not worried about hurting the bathtub, right? It's about the people in the bathtub. That's because you are full of dissolved ionic compounds. Fact is, when you sweat them out. They call it electrolytes. You've got a whole bunch of ionic compounds dissolved in you. So you conduct electricity really well. The electricity would much rather go through you than go through the water. So that's what makes it dangerous. If it went through the water really well, it wouldn't be dangerous. The problem is it doesn't go very well. Instead, it'd rather go through you. And those electrical signals mess up your heart. Heart stops beating. Tends to lead to some bad things. I never hear anybody complain about it. Oh, no. Okay. So, now we take some salt. Pour it in. So putting the salt in there made the water like the metal. Made the light bulb come on. So is the salt making the electricity? No, it's just letting the electricity pass through it. Because electricity is moving charges. When I throw it in the water, the salt dissolves. We know that because it goes everywhere in the water when we rinse our mouth out with salt water. I do when sometimes we get a cold sore. Okay? The salt goes everywhere. It's broken up so it can move. So dissolved ionic compounds can conduct. So if I melt them, which I'm never going to see because the temperature is way too high, or if I dissolve them in water. And this is actually the test that they do to decide whether it's ionic or not. So they throw it in water and see how well it conducts electricity. Say, well, everything's going to do that. Well, not everything. Okay, got some fresh water. Put my light bulb back in, still not on, because it's now just the water. And now instead of salt, I'm going to put sugar. Now sugar is carbon, hydrogen, and oxygen. Last year you talked a lot about glucose, C6H12O6. A couple of glucoses stuck together is sucrose, C11H22O11. But no metal, carbon, hydrogen, and oxygen. So I put sugar in the water. The light bulb doesn't go on. So is that because sugar doesn't dissolve in water? No, because we all know the sugar goes everywhere in the water, right? So it's dissolving, which means the sugar moves around, but it's not conducting because the pieces don't have charges. You got to have both pieces. You got to have moving pieces with charges. Sugar has the moving pieces. It doesn't have the charges. Solid ionic compounds have the charges, but can't move until I dissolve them or melt them. So if I were to grab some baking soda, well, I was going to grab it and somebody grabbed it for me. and took it home. Yeah. Where'd my baking soda go? I had a big box of it. No, they literally took it. So, all right. Well, oh, there it is. So, baking soda, is it ionic? You don't have to. The official test? Is baking soda ionic? Yeah. So see how the sugar didn't do it, but the baking soda makes it happen. You also notice that I'm using a glass stirring rod because glass is a good insulator. I did not use the piece of metal to stir with because then the electricity would go through me rather than the bulb. Okay, so that's how ionic compounds conduct. They get torn apart into charged pieces. Okay. Our last topic, ooh, he said last topic, before our test next week, is how metals behave. Last chapter, we talked about metals as things that conducted, were malleable and ductile, gave away electrons, didn't hang on to electrons very well. That's how we describe metals. So now we're going to use what we know about atoms to explain those pieces. So the metallic bond is how the atoms are held together in a solid. Because we got to explain why this conducted. And we said conducting is moving charged pieces. What's moving? What's charged in a metal? Okay. We know this conducts, so we know it has to have moving charged pieces. So however these metals are hooked together, charged pieces have to be able to move. Otherwise, okay? And the piece that moves is the piece they don't hang on to. The valence electrons. Metals let go of their valence electrons. They've got low ionization energies. Easy to remove the electron. They have low electronegativities. Don't pull hard on anybody else's electron. So the way scientists describe metals is picture them as not being neutral. Picture them as the ions already. And the valence electrons can move anywhere between any of those ions. They call it the sea of electrons model. Positive ions floating in a sea of electrons that the valence electrons are able to move through. Sea of electrons. The electrons are able to move. Electrons have a charge. They're able to move. Metals conduct electricity. But for a metal to do it, the whole ion doesn't move, just the electron has to move. Ionic compounds, the whole ion has to move. Metals, just an electron. So picture them like this. This would be what a piece of sodium would look like. It would have one positive ions and negative electrons that can float anywhere between them. Can you tell which atom lost which electron? No. So it doesn't care which electron's next to it, as long as there's electrons in between together. Because what's holding these two together is they're both hanging on to that. If I had something like calcium, calcium's going to have a 2+ ion and extra electrons. Okay? So how the atoms are in a piece of metal. That you've got positive ions with negative electrons able to float. Okay? And that's going to explain why they conduct, why they're malleable, and why they're ductile. Okay? It actually explains why they're shiny. Shiny means they reflect all the light back at you, right? Where can those electrons be? Those electrons can be anywhere, which means they can have any energy. Which means the light that hits them, they can reflect back with any energy. So you can see all the lights that hit it. So it gives you a shiny reflection. Okay. More on that on Monday.